Hello, am I audible? Hello.
Yeah, ma'am.
Okay. So today is the second revision session for quiz 2. The session will cover week 7 and week 8, both the theoretical aspects and some of the examples. So let's wait for 5 or 10 minutes more. We'll start at 4:10, okay, so that others can join. I think so I have discussed the blueprint for week 2. Right? So you know that every week contains at least 20% of the weightage. So there are some questions from week 5 to 6 and then 7.
Ma'am, your voice is not proper.
Yes,
Still
ma'am.
it is not clear.
Yes, ma'am. It's not clear.
Hello, is it clear now?
Yes, ma'am. Better. Ma'am.
Okay, so let's start with some introduction. So in today's session, we will cover some of the topics which are from week 7 and week 8. So from week 7, we'll start with basic theory of series. That means what is a series, what do we understand by convergence of series, and what are the tests we have to find out that a particular series is convergent or not. So there are majorly three tests we have: comparison test, the ratio test, and root test. So we'll explore tests in detail. So I have one example here. So we'll take that example and find out the convergence and divergence of this particular series, right? So this is the example I have. So I'll give you guys 5 minutes to solve this question, and then we will discuss it in detail. So after that, we'll move to power series. So we'll understand what is a power series, how can we find out the convergence and divergence of a particular power series, and by that means the radius of convergence of a power series. Because we know that in a power series we have a variable x. So what we have to do, we have to find out those values of x for which this power series will become a convergent series. Okay, so we'll take a power series, we'll put one value of x, and then judge that given series on that value of x is convergent or not. And we have actually quite an easy test for finding the convergence of power series, which is the ratio test. So we'll use the ratio test, we'll study ratio test, and then we'll use the ratio test to find out the radius of convergence of this particular series. Okay, and after that, we know that why we jump into this business of power series. So the reason is we want a function whose derivative is itself. So that means we want f dash of x to be equal to f of x. So we want to find a function which possesses this particular property, and using the power series we actually define a function named to be exponential function. So we see that if you compute the derivative of e to the power x, it will become e to the power x itself. So the power series give us the answer that okay, there is a function with this property that its derivative is itself, and that function is known to be exponential function. So we'll see some of the properties of exponential function. That means how this function behaves. So what are the limiting properties? What are the continuity, differentiability of this particular function? Okay, so that's all about week 7. So till this portion we have week 7, and then we'll jump into week 8. So we know that when we jump into week 8, we start with integration, right? So the basic problem is to find the area under the curve. So for solving this problem, that means finding the area under the curve, we define Riemann integration. So we'll study Riemann integration. So there are three types of Riemann integration we have introduced in our course. That is left Riemann integration, right Riemann integration, and mid Riemann integration. Let me clear this. Okay, so now we will study these three Riemann integration, and we also try to find the left Riemann integration, right Riemann integration, mid Riemann integration for this simple function f of x is equals to 3x minus 4. And after that, we will go to the definite and indefinite integration. So what is definite integration? We know that definite integration is nothing but the Riemann sum, the limit of Riemann sum. Right? So this is the limit n goes to infinity of R, N, F, and whatever partition we have, this type of thing. Right? So we'll connect definite integral and indefinite integral. Indefinite integral means that integral which is defined by antiderivative. Okay, so using fundamental theorem of calculus, we know this result, that integration a to b f of x dx is nothing but f of b minus f of a. And here we have capital F. This capital F is actually the antiderivative of a small f function. Right? So these all things we already know, but we will revise them. And then we will solve one question to how about the technique of integration. So there are actually two techniques. One is the method of substitution, and another one is the method of integration by parts. So we'll revise these two methods and then try to solve this particular integration. Okay, so this is the blueprint of today's lecture. So let's start. Is there any doubt from the previous lectures or anything which is not clear so far? You guys can just unmute yourself and ask. Okay. And if there is any lag from my side, just let me know in the chat, or you guys can unmute yourself and tell me. So let's start with the first thing, which is the series. So what is a series? So series is nothing but we are summing infinitely many values. So that means if I say that 1 plus 2 plus 3 plus 4 plus and so on, then this is nothing but a series. Right? So a series is nothing but the sum of infinitely many terms. So we know that using infinitely many terms, we also we can consider those infinitely many terms in terms of sequences. So I'll say that I have a sequence an is equals to n. So that means a1 is equals to 1, a2 is equals to 2, a3 is equals to 3, and so on. And what I'm doing, I'm summing infinitely many terms of this sequence in this particular order. So that means I'm saying that summation of an when n is ranging from 1 to infinity is nothing but 1 plus 2 plus 3 plus 4 plus and so on. So a series is nothing but the sum of terms of sequences also. Right? So you can say that a series is nothing but the sum of infinitely many terms, but we can use that those infinitely many terms to define a sequence. So ultimately a series is nothing but the sum of terms of a sequence. Okay. So now as we involve this particular sequence in the series, now what is the question here we want to ask? So we want to ask that if we sum these many terms, is it possible to get a finite number, or is it possible to say that this sum will never converge to a finite number? Okay, so that means here the basic question we want to answer is all about convergence. Convergence means, is this sum leads us to a finite number or not? Okay, so this is the one thing we want to judge. So for that, what we do, so we will define a sequence related to series, and then we will say that if this particular sequence converges, then our series will also converge. So what is that sequence? That sequence is known to be the sequence of partial sums. Okay, so suppose now we have a series. So suppose summation n is ranging from 1 to infinity an, which is a1 plus a2 plus a3 plus and so on, is a series. Right? Then we say Sn is a sequence of partial sum. So here we can simply say that Sn, this Sn is a sequence of partial sum, where what is this Sn? So this Sn is nothing but the sum of first n terms. So that means S1 is a1, S2 is a1 plus a2. That means sum of the first two terms. S3 will be sum of the first three terms. That means a1 plus a2 plus a3, and so on. Sn is nothing but the sum of the first n terms. That is a1 plus a2 plus a3 plus and so on plus an. So now here we got a sequence related to a series. So that means initially we have a series summation here. Using this series, we have defined a sequence Sn. Right? Then what we will do, so we will say that this series converges to S if this S is nothing but the limit of sequence Sn. So that's how we define the convergence of a series. That a series will converge to a number s if this s is nothing but the limit of sequence of partial sum. Why partial sum? Yes, so this sequence is also known to be sequence of partial sum. It is there in the definition. So ultimately, we define convergence of a series using the convergence of this particular sequence of partial sum. Okay, so any series converges to a number if that number is the limit of its sequence of partial sum. And we know it partial sum means the sum of the first n terms. So Sn is the sum of the first n term. So this is the definition of convergence of a series. This is the basic definition of convergence of the series. But we never uses this definition to find the sum of any series. Okay, so what we will do, so we have some tests to finding that a series is convergent or not. So what is the meaning of convergence of a series? So we say summation an converges if. So converges means if this particular limit, that is limit n goes to infinity of Sn, is a finite number. Right. So we say that a series is convergent means it converges to a finite number. It converges to a finite number means the limit of its partial sum sequence is a finite number. This is the meaning of convergence of a series. Now we have actually three particular tests we can using which we can judge a series is convergent or not. Right. So the first test is the comparison test. But before this, in our lecture, we have discussed a geometric series. So we know that what is a geometric series. So let's quickly recall that geometric series. The geometric series is a series of this particular type, that is summation a n r to the power n. This is nothing but a plus ar plus ar square plus ar cube plus and so on. Right? So this is the this type of series is known to be geometric series with ratio r. Right? With ratio r. So here what is special in this r? So here if you divide the previous term by the second term or the second term by previous, you will get something related to r. So that means if I take ar by a, I'll get r back. If I do ar square by ar, I'll get r back. Right? So this common number is known to be the ratio of geometric series. So if we have a geometric series with ratio r, then we know that then the series summation summation a r to the power n actually converges if the modulus of r is strictly less than 1. Okay, so if you take modulus of r is strictly less than 1, then this geometric series converges. And the reason behind this, we have already studied in lectures. So we some kind of relate the convergence of series with some sort of sequence. So you can just go back into the lectures and recall that particular proof. Okay, so by that particular proof, we can say that a geometric series summation a and r to the power n converges if modulus of r is strictly less than 1, and it diverges if modulus of r is greater than or equal to 1. Okay, so this is a very well known and standard result about the geometric series. So if you have a geometric series with ratio r, then that particular series will converge if modulus of r is strictly less than 1, and it will diverge if modulus of r is greater than or equal to 1. Okay, and the reason behind this we have already covered in the lectures. So let's recall again. So what we have done so far. So we know that what is a series? Series is sum of infinitely many terms. How we are saying that a series is convergent or not? So we are actually associating a sequence to a series, and then by the limit of that sequence, we are telling that a series is convergent or not. So we are saying that if summation a n converges, that a series is convergent if the sequence of partial term is a finite number. That means limit n goes to infinity, Sn is a finite number. Now we recall the geometric series. So if we have a geometric series with ratio r, then geometric series will converge if modulus of r is strictly less than 1 and diverges if modulus of r is greater than or equal to 1. Okay, so let's take one example with geometric series. So suppose I'll ask you, does the series summation 1 by 2 to the power n converges or diverges? Okay, so let me see what you guys think about this question. So just answer in the chat, or yeah, just answer in the chat. Yes or no. So what do you think? This series converges? If it converges, write yes. If it diverges, write no. So there are almost 24 people, so I need at least 10 answers. Then only I'll move ahead. Okay, converges, yes. Okay, good. So here it's kind of easy that what is this series? This is summation 1 by 2 to the power n. That is 1 plus, if I start with 0, if you start with 1, doesn't matter. So it's 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube and so on. So this is nothing but a geometric series with ratio r to be equal to 1 by 2. And what is modulus of r? Modulus of r will be modulus of 1 by 2, which is 1 by 2 and which is strictly less than 1. So from the previous result, since the ratio is strictly less than 1, this series will converge since it's a geometric series. Okay, it's a very kind of easy type of questions if you know the geometric series very well. So now let's go to the next test, which is the comparison test. So comparison test is actually kind of a little tough to apply, because in this test we need some other series to compare our given series, and we should know the other series' behavior, is that series converges or not. So until and unless you have a kind of good set of series by which you know that these series converges or diverges, then only you can apply this comparison test. Okay, so let me state what is a comparison test is. So there are two statements. So first statement is, if we have a series whose modulus of an, that means whose terms are less than or equal to some another term series, which is known to be Cn. So if we have modulus of an is less than or equal to Cn, almost for all n belongs to natural numbers, or after certain finite stages, and if this term series converges, that means if summation Cn converges, then we will say summation here also converges. Right. So here it is kind of obvious, until and unless you find a series with this property. That means first thing is this particular summation an should be that modulus of an should be less than or equal to Cn, and the second thing is the Cn should converges. So until and unless you have such type of series, you cannot apply the comparison test. It's very good test if you know a good set of series. So the first statement says, if modulus of n is less than or equal to Cn for all n belongs to natural number, and if summation Cn converges, this will imply summation En converges. So I would like to take one example here. So example is, what can we say about summation 1 by n to the power 3, this series? Right? Is it convergence or divergence? Okay, so here we will try to use a comparison test. So we know that, or else what can we do? We will have series 1 by n cube plus 1. Okay, because here we will use the 1 by n to the power p type of series, right? So we know that if we have a series like summation 1 by n to the power p. Okay, so this is known to be the p series. P series means summation of 1 by n to the power p. So here your summation starts with 1 to infinity. So we know that this type of series converges if this p is strictly greater than 1. So that means 1 by n square, 1 by n cube, 1 by n to the power 4, and so on. These type of series actually converges. And it will diverges if the value of p is less than or equal to 1. Okay, so this is known to be a p series. And this is a very, obviously very famous result about p series. So if we have a series of the type summation n is ranging from 1 to infinity, 1 by n to the power p, then these series converges if the value of p is strictly greater than 1, and it will diverges if the value of p is less than or equal to 1. Okay, so we'll use this result to find out the convergence or divergence of this particular series, summation 1 by n cube, 1 by n cube plus 1. Okay, so here we use the basic logic that we know that since n belongs to natural number, the value of n cube will always less than n cube plus 1. which is kind of obvious because n belongs to natural number. You will take any natural number, make it cube, and if you add 1, then obviously that value will be bigger than the value of n cube. So n cube is strictly less than n cube plus 1. But if you take the reciprocal, that means 1 by n cube. Now here the inequality changes from strictly greater than strictly less than to strictly greater than. So the value of 1 by n cube is strictly greater than 1 by n cube plus 1. Okay, and this happens for all natural numbers. So that means what do we have? We have that 1 by n cube plus 1 is strictly later than strictly less than 1 by n cube, right? So this is our an, and now this 1 by n cube can work as a cn, and more than that we have that summation 1 by n cube converges. Why it converges? Because of the p series. So here the value of p is, so since p is equals to 3, which is strictly greater than 1, so this will imply summation 1 by n cube converges. So here we have a series which kind of dominate the terms 1 by n cube plus 1. So now by comparison test, we can say that the summation 1 by n cube plus 1 converges. Okay. So that's how you can use the comparison test. And more or less, whenever we have to use the comparison test, you obviously need to remember this p series test. It is very it is very applicable. It is used more than 70%. So there are several series which you can compare just by such type of series, 1 by n to the power p. Okay. So now here let me ask you one question. So example. It's kind of similar type of example, that is the series summation 1 by n square plus 2n plus 1 converges or not? What will be your answer here? So if we have a series summation 1 by n square plus 2n plus 1, now does this series converges to a finite number or not? Okay, so again type yes if it is converges or no. So I'll give you 1 minute to think. Yes, correct. So as you guys said, it will converge just because of the same reason. We can compare this particular series with the series 1 by summation 1 by n square, right? And we know that summation 1 by n square converges. And by comparison test, you can easily guess that 1 by n square plus 2n plus 1 is actually strictly less than 1 by n square for all n belongs to natural number. So by comparison test, we can say that this particular series will also converges. Yeah, okay. So that's how we can use the first statement of comparison test by finding a series Cn for which modulus of An is less than equal to Cn and summation Cn converges. Okay. Now there is another statement of the same comparison test, the second statement. So it says that if you find a series like this, that if 0 is less than equal to some dn is less than equal to an, and here we want summation dn to be diverges, then the summation en also diverges. Okay, so here the result says that if we are able to find a series summation dn in such a way that the terms, that means the dn is actually less than or equal to an for all n above some number or for all n belongs to natural number, and the series summation dn diverges, then you can say that summation en also diverges. Okay, so here we can take one example. So suppose I'll take an example like, so what about the nature of summation 1 by n minus 1? Is the series converges or diverges? Okay, so here we know that that n minus 1 is strictly less than 1, strictly less than n, and this will imply that 1 by n minus 1 will be strictly greater than 1 by n. So this 1 by n can work as dn for us. So here we have that an is strictly greater than dn, which is greater than equal to 0, and the summation 1 by n diverges just by the p series. Okay, so by the comparison test, we can say that summation 1 by n minus 1 also diverges. Okay, so that's how we can use the comparison test if we know the p series test. Okay, so we can compare such type of series with p series, and then we can easily judge that a given series converges or not. Okay, but again, the uses of comparison test is not that much if we compare it with the ratio and root test. So we mostly apply ratio and root test for finding the convergence and divergence of a series. So at the end, I'll discuss the pathway, that how you should proceed if you have a series given and if they ask you about the convergence and divergence. But first, recall what is a root test and ratio test. Okay, so root and ratio test. So first, let's see what is a root test. So in root test, we want to find out this particular limit, that L is nothing but limit n goes to infinity of modulus of an to the power 1 by n. Okay, so if this limit exists, and if the value of L is strictly less than 1, then we will say summation an converges. If the value of L is strictly greater than 1, then we will say summation an diverges. And if the value of L is equal to 1, the test actually fails. We don't have any conclusion in this particular case. Okay, so this is known to be the root test, right? Why root test? Because we are finding the nth root of the modulus of n. That's why root test. So in the root test, first thing we have to do is calculate this limit. That limit n goes to infinity, modulus of an to the power 1 by n. And if this limit exists, we will see what is the value of L is. So if the value of L is strictly less than 1, then the series converges. If the value of L is strictly greater than 1, then the series diverges. And if the value of L is strictly equal to 1, we cannot say anything about the series. Now we have an example here, that summation 3 to the power n upon n plus 1 to the power n. So I'll give you guys 3 minutes or 4 minutes to solve this question. So is the series, or we can say that what will be the result if we apply root test on summation g to the power n upon n plus 1 to the power n is ranging from 1 to infinity. Okay, so here you have three options. A is converges, B is diverges, and C is the test will fail. Okay, so let's take some time here, up to 4:35. So try to solve this question on your own, because until and unless you will apply, until and unless you practice something, there is no way you can get the questions in the exam. Okay, so let's try to figure it out for 3 to 4 minutes, and then we will discuss this question. Okay, and also answer in the chat box so that I will know how many people are attempting or not. Okay. Okay, so we have some answers here. So let's try to see what will be the. So again, it's kind of obvious that we have to apply root test. And why is this so? Since I have given, and also you can easily judge by the expression that we have 3 to the power n. So if you take the nth root of it, it will reduces to 3, right? And we have n plus 1 to the power n. So again, if you take the nth root of this term, we will get n plus 1. So it's kind of obvious to apply root test here. So in root test, what we need to find out? We need to find out L is equals to limit n tending to infinity of modulus of a n to the power 1 by n, right? So let's see what is this. So limit n goes to infinity, modulus of a n, but the value of a n is 3 to the power n upon n plus 1 to the power n to the whole power 1 by n. Okay, so here this modulus won't affect the term because again we have all positive terms. 3 to the power n will be positive since n belongs to natural number, n plus 1 to the power n, that was also positive. So that means this modulus is nothing but limit n goes to infinity of 3 to the power n upon n plus 1 to the power n to the whole power 1 by n. And if we take the nth root of both numerator and denominator, we will get limit n goes to infinity 3 to the power n to the power 1 by n, which is nothing but 3, and upon n plus 1 to the power n to the whole power 1 by n, which is nothing but n plus 1. Right? And this limit is kind of easy. As n goes to infinity, this whole term will go to 0. Right? So the value of L is nothing but 0. Here we will get L is equals to 0, which is strictly less than 1. So by root test, we have that summation n converges. Okay, so the answer is A. That means this series converges by root test. Okay, so if it is not given to you that apply root test or not, you have to judge by your own that which test you have to apply. So it's by the expression of the term, you can easily say that since there are powers of n, so if we take the nth root, it will cut the power of n, and we will get a simpler expression, right? So it's kind of obvious to apply root test here. So I hope that is clear. If you guys have any doubt, you can ask. You can stop me and ask. Okay. So now this is all about root test. So now it is a ratio test. So in ratio test also we have to compute a limit, and then by the value of limit we have to judge whether the series converges or not. Okay. So in ratio test, actually what happens? So the value of limit n goes to infinity, modulus of a n plus 1 upon a n. This is same as the value of limit n goes to infinity, modulus of a n to the power 1 by n, if both limit exist. Okay, so if exist. So if both limits exist, their value is similar. So since we are getting the value of L to be same as the root test, the root test, so that's why the result will be same here. So that means if the value of L is strictly less than 1, we can say that summation En converges. If the value of L is strictly greater than 1, we can say that summation En diverges. If the value of L is equals to 1, we will say the test will fail. Okay, so this is same as the what you can say the root test. Okay, since if both limits exist, their value will become same. That's why. So this is known to be the ratio test. Now we have one remark. So this remark says that. If the summation En converges, so that means if we have a convergent series, we can say that the limit of sequence En is nothing but 0. That limit n goes to infinity of En is nothing but 0. So this is a well-known remark, because if limit n goes to infinity, En won't become 0, then we are adding something in. We are always adding something in our series, so it can't converge to a finite number, right? So that means if we have a convergent series, then limit n goes to infinity of En also always becomes 0. So suppose a series is given to you, and they will ask about convergence or divergence. So what we have to do? So first step is to find the limit. That limit n goes to infinity is En is 0 or not. Okay. So if it is 0, then we have to proceed further. If it is not 0, then we will say diverges. So if limit n goes to infinity, En will become 0, then we'll proceed further, and then we will go to ratio test. If ratio test is applicable, then that's okay. If not, we will go to root test. And at the end, if root test won't work, we will go to comparison test. Okay, so this is a pathway you should apply if you have any series given to you. And the question asked was that particular series is converges or diverges. First thing is you need to check that limit n goes to infinity a n is 0 or not. Because if it is not 0, the series can't converge. So it will become a divergent series. Then if this is true, then we'll go to ratio test. If ratio test give us some answer, then it's okay. If not, then we'll go to root test. And then after we go to comparison test. Okay. So now there is one reason why we are taking ratio test before the root test. Because what happened, root test is little bit stronger than the ratio test. It is possible to get an answer because of the root test if you won't get an answer by ratio test. Okay. So the reason behind this is actually the strongness of limit n goes to infinity modulus of a n to the power 1 by n. So sometimes it is possible that this limit exists, but the ratio limit does not exist. Okay. So this detailed thing you can learn if you go to some higher mathematics courses. But just keep in mind that the root test is a little bit stronger than ratio test. Okay, so it is possible that ratio test might fail, but root test will give us the answer. So currently, I actually don't have an example where root test work, but ratio test doesn't. But let's see, we can discuss it in meantime. Okay, so this is the pathway you should apply if you have any series. Now let's talk about power series. So what is a power series? So power series concept we introduced to find out an answer for the question that we want to find out a function whose derivative is itself. Okay, so then we take a polynomial, then we try to find out its derivative and compare the coefficient and all those things we have done to find out functions for which this could be true. And the answer is, if we take a function f of x is equals to 1 plus x square by 2 factorial plus x cube by 3 factorial plus x to the power 4 by 4 factorial plus and so on. Right? So that means if you define a function like this particular series, then then it's kind of easy that f dash of x is nothing but f of x. Okay, so that means a power series is giving us the answer. And this function is nothing but e to the power x function or exponential of x function. Okay, this is also known to be e to the power x. So what is a power series? So power series is a series with a variable or with some unknown thing which is given to us. So that means summation a n x to the power n. Such type of series is known to be a power series. Right? Where here x is nothing but a variable. So variable means the value of this particular thing can depend situation to situation, or it's depend on the terms here. So these type of series are known to be a power series. So whenever we have a power series, what will be the natural question to ask is on what values of x this particular power series converges. Okay. So here the question we want to ask answer is on what values of x this series converges. Okay. So for example, I'll take a simple power series. Suppose I have summation some 3 into x to the power n. Okay, so suppose this is our power series and is ranging from, I can take 0 to infinity. Okay, so now this is one type of power series. Right. So now here observe that if I substitute different values of x, what will happen to this particular power series? If I substitute x is equals to let's say 1 by 3. Okay. So then what will happen? Then the power series will become summation n is ranging from 0 to infinity 3 into 1 by 3 to the power n. Okay. So now you observe that this is nothing but a geometric series. Geometric series with ratio. What will be the ratio here? The ratio will be 1 by 3 because we are taking 1 by 3 to the power n. If you compute the series, it's nothing but 3 into 1, then plus 3 into 1 by 3, then plus 3 into 1 by 3 square, and so on. Right? So here the ratio is 1 by 3, which is strictly less than 1. So that means on x is equals to 1 by 3, this power series converges. But instead of 1 by 3, if I take 3, if I take x is equals to 3, then the power series will become summation 3 into 3 to the power n. which diverges because of the quite reason we don't have here limit n goes to infinity, an is not equal to 0, right? We have 3 to the power n, so limit n goes to infinity. So limit n goes to infinity, 3 to the power n goes to infinity. Okay, so at x is equals to 3, it does not converge. That means divergence will happen. So there is so that means the question is kind of obvious that we actually need to find out the values of x for which the particular power series converges or not. So that means if you substitute that value of x, then your series converges or not. Okay, so what are those values for which this power series converges? So ultimately it's nothing but an interval. So that means if you collect the whole set of values for which given power series converges or not, actually become an interval. So for finding that particular interval, or we have a term related to that which is known to be the radius of convergence. Okay, so what is the radius of convergence related to a power series? So radius of convergence. So radius of convergence means if we have a power series summation a n x to the power n, then a particular number r is said to be, this r is called to be radius of convergence. That is RC, we can write radius of convergence. If modulus of x strictly less than r will imply the summation a n x to the power n converges. And if you take any value of x which is whose modulus is strictly greater than r, then your series summation x to the power n diverges. Okay, so that means r is that number around which, so over the real line, if you want to think about it, so it's nothing but a type of interval, in such a way that if you take a value of x in such a way that modulus of x is strictly less than r. So here you can assume that this distance is r. So if the value of x is strictly less than r, that means if you find if you take any x in between this particular 2r interval, right? R plus R2 r, that's why radius we know. So diameter we have, right? So if radius is r, the diameter will become 2r. So if you consider a circle, so in place of circle we have an interval here. If you take any value of x in between this particular interval, on that value the power series actually converges. But if you take any outside value of x naught, then on this one we have modulus of x naught greater than r, and the series actually diverges. Okay, so this is known to be radius of convergence. So now we have a root test similar whatever we have discussed now. Similar type of root test we have to find out the radius of convergence of a power series. So let's see what is that root test is. Okay, so if we have a series summation e n z to the power n or x to the power n, then the radius of convergence, that is 1 by r, is nothing but limit n goes to infinity of modulus of a n to the power 1 by n. So that means this limit is known to be 1 by r. Okay, so here we are assuming that this limit is not equal to 0. And if limit is equals to 0, if limit n goes to infinity, modulus of a n to the power 1 by n, if this is equal to 0, we can say r is equals to infinity. The reason behind this is we don't know what is the reciprocal of 0, right? 1 by 0 does not make sense. That's why we have written down if this limit will become 0, then our the radius of convergence will be infinity. And if this limit is not 0, it will be the reciprocal of it. Okay. Yeah, I'll write a bit slow. Okay, so this is known to be the root test. So now I have an example, and we will find out the radius of convergence of that particular series. So let me see that example. Yeah, so we have this one here. So now the question is to find the radius of convergence of this particular series. Okay, so let's try to solve this one. Or else I'll give you guys 2 minutes to find the radius of convergence by your own, and then we will discuss it. Okay. So try to solve it by your own, or at least give a hand on this question. So here you might need the limit, that limit n goes to infinity of n to the power 1 by n is actually equals to 1. Okay. So this limit you can prove by L'Hospital rule. If you use L'Hospital rule and a little bit of log function, then I think you need this limit to answer this question. Okay. Okay. So let's see how we can solve it. So we have to apply a root test. That means we need to find out limit n tending to infinity modulus of a n to the power 1 by n. What is this? This. Okay. So first of all, figure out what is a n. So if we have summation a n x to the power n to be equal to summation minus 1 to the power n cube x to the power n upon 3 to the power n, then here this whole quantity is our a n. Right? So our a n is nothing but minus 1 to the power n cube upon 3 to the power n. So if a n is minus 1 to the power n cube upon 3 to the power n, then what will be modulus of a n, right? So again, we need to compute modulus of a n to the power 1 by n, not a n to the power 1 by n. Okay, so there is a little difference between a n and modulus of a n. So whenever we take modulus, such type of terms which are giving us negative quantity will vanish, right? So here modulus of minus 1 to the power n cube upon 3 to the power n, this will become only n cube upon 3 to the power n. right? Because minus 1 to the power n will vanish because of the modulus thing. So that means here modulus of an is nothing but n cube upon 3 to the power n. Now again what we need modulus of an to the power 1 by n. So here modulus of an to the power 1 by n will become n to the power 3 by n, and again upon 3 to the power n upon to the power 1 by n, right? So this will become n by n only. So which is nothing but n to the power 3 by n upon 3, right? So this is our modulus of n to the power 1 by n. So now what we need to compute? We need to compute that our radius of convergence will become 1 by r is nothing but limit n goes to infinity of modulus of an to the power 1 by n, which is nothing but limit n goes to infinity of n to the power 3 by n upon 3. Okay, so here I have given that limit n goes to infinity of n to the power 1 by n. This is actually nothing but 1. But since it's equal to 1 and we need n to the power 3 by n. But what is this? This is nothing but n to the power 1 by n, the whole cube you can say. Right? And the cube function respect the limit. So that means if this limit is 1, we can say that limit n goes to infinity of n to the power 3 by n is also the 1 to the power 3, which is nothing but 1 only. Right? So here the upper limit goes to the upper that means the numerator goes to 1, and in the denominator we have 3. So but 3 stay as it is. So here we can say that this limit is nothing but limit n tending to infinity of 1 by 3, which is nothing but 1 by 3. So the value of 1 by r is equal to 1 by 3, which implies the value of r is nothing but equal to 3. Okay, so here we get the radius of convergence is nothing but 3. Okay, so is that clear? Any doubt in this question? Sir?
There was x to the power 3 as well, x to the power n on this question.
Yes, Sudhanshu, but whenever we talk about power series, we just need to focus on an, not the variable's power, right? So in the result also, so when we discuss the root test here, so here is the power series summation an x to the power n, and we need to compute the limit n goes to infinity of modulus of an to the power 1 by n. Okay, so whenever we have a power series, we actually ignore this variable's factor x to the power n. Okay, but if you have a normal series, then you have to consider it. But in power series, we remove this x to the power n. Okay. So that's all from week 7. One thing we have which is exponential function. So let's quickly decide what is the exponential function is. What are the behavior of exponential function? F of x is equals to e to the power x. Okay. So the behavior of exponential function is increasing behavior. So that means this is the graph of e to the power x. It will intersect the y-axis at the point 0, 1. Because we know if you substitute x is equals to 0, we'll get the value e to the power 0 will be 1. And it is an increasing function over the whole real number. Right? It is increasing and it's going towards infinity. So here we have some properties. So first property is that e to the power x is an increasing function. Okay. Second property we have the limit. So that means limit n goes to infinity, e to the power x is actually infinity. Sorry, limit x goes to infinity, e to the power x is actually infinity. Because we can observe by the graph, if it goes toward infinity, the graph is going also towards infinity. Right? And the second limit we have, that limit x going to minus infinity, e to the power x is actually 0. Right? So here if we approach towards minus infinity, the graph is approaching very closer to x-axis. So that means the value of function is approaching to 0. So limit x goes to minus infinity, e to the power x is nothing but 0. So these are the two end behavior we have of the function e to the power x. The another thing about this function is the derivative of this function. That means the derivative of e to the power x is actually e to the power x itself. So this is the one function for which we have the property that its derivative is nothing but the function itself. Okay. So these are the properties we have. So another thing is the value of e to the power x will always strictly greater than 0 for all x belongs to real number. These things you should know, that no matter whatever the value of x you will take, the value of e to the power x will again positive number, because we know that e is a number which lies between 2 and 3. So the power of that number will again positive. Okay. So these are the small things about the exponential function. Now let's move toward the Riemann sum. So what is the Riemann sum and how we interpret the Riemann sum with area under the curve. So Riemann sum. So suppose I have a curve and I want to find out the area of this particular curve. So suppose I have a curve like this. This is our f of x. I want to judge what is the area under the curve. So the basic thing is, we know that what is the area of a square. Right? The area of a square is nothing but the square of the any length, right? So if the length is l, the area will be l square. So now what will be the area of a rectangle? So what we will do, we can decompose this rectangle into squares and then find out the area. Right? Now what will be the area of triangle? So we will make a rectangle out of this triangle and then find out the area. Right? So these are the things we usually do if we know some areas and want to find out the area of some unknown figures. Right? That means we know the area of square. To find out the area of rectangle, we decompose the rectangle into some squares and then find the area. If we want to find the area of triangle, we'll create a square out of that triangle or create a rectangle out of that triangle and then find out the area. So same thing, same approach you will use here. So we will decompose this area into some area of rectangles. So for a rectangle, so if you have a rectangle here, so for a rectangle, there are two quantities we need to know. One is the length of that rectangle and another one is the breadth of that rectangle, right? So what will be the value of L? What will be the value of B? We need to consider for any rectangle. Okay. So what we will do here, so we will take the breadth to be the values taken by the values over the interval 0 to, suppose this is 0 to some a. So we'll take this particular length to be breadth. So what we'll do, we will find out some points between 0 to a, and the difference between each points, the difference between those points are known to be the breadth of the given rectangle. So that means I'll select some points from 0 to a, and whatever distance here we have, I'll select that distance to be breadth of my rectangle. Okay, so for breadth, we are selecting this particular value. And for length, what we can select? Okay, so for length, what we will select? So for length, we will select the value of function at any point in between this particular interval. So suppose this is 0 to some, you can take any number. So let's take it from 0 to a1, then a2, a3, up to this is going to be b. This is here. Okay. So the idea is to decompose this area into some set of rectangles, and for rectangles we need two values. We need the value of L, we need the value of B. So for the value of B, we are taking the length of this subintervals, and for the value of L, we are taking the value of function. But here we have some choices over the value of function, right? You can take value of function to be f of 0. I'm talking about the small interval 0 to a1. So you can take f of 0 as your height or as your length of rectangle. You can take f of a1 too. You can also take f of 0 plus a1 by 2, right? The middle point as your height. Or you can take any f of xi, where the xi is a part of open interval 0 to a1 or close interval 0 to a1. Right? So that means we can take any value of a function as the height of our rectangle. So what if I'll take 0 as the height of rectangle? So then this will be my first rectangle. 0 means I am taking the left end point of each subinterval, right? So here we have a1, a2, and then if I take a2, then a3. If I take a3, then something like this. Okay. So you kind of observing that this area is nothing but under this area of whole rectangle. So that means if you add the area of each rectangle, you'll get that the area of region is nothing but lesser than the area of sum of all rectangles. Okay. So here what we will do, we will shrink this particular distance, right? So we will shrink these distance. Okay. And we will shrink this distance, and ultimately as we approach us to infinity, that means if we consider infinitely many subintervals between 0 to a, we kind of assume that the area is given by the limit, and that limit is known to be Riemann sum. So we have already discussed it, but this is the basic theory about Riemann sum. Okay, so now there are we have three types of Riemann sum: left Riemann sum, right Riemann sum, and mid Riemann sum. So let's discuss one by one. So what is the left Riemann sum? Okay, so left Riemann sum means, suppose we have a function, suppose f is a function, and we want to divide close interval a comma b into n regular parts. Okay, so whenever we want to divide a closed interval into n regular parts means we are taking the length of each regular part. So then length of each part will be a plus b by n. Okay, so that means if you are dividing 0 to 4 into 3 regular parts, the length will be 4 minus 0 by 3, right? Or 4, if you divide it into 4 regular parts, the length will be 4 minus 0 by 4, that is 1. So when we divided it into n regular parts, we have some n numbers, right? So if you divide this closed interval into n regular parts, a comma b, you have some numbers here, right? So first part will be some a comma, so this a also written as x naught. So x naught comma x1, and this is same as the second part will be x1 to x2, right? The third part will be x2 to x3, right? And so on. The last part will be xn minus 1 to xn, and this xn is also equal to b. So any interval we can divide into some regular parts, and the length of each regular part will be 1 by n. So that means here the difference between x2 and x1 is also a plus b by n. The difference between any two, the length of each subinterval is nothing but a plus b by n. Oh, sorry, b minus a by n. I have written this is wrong. This is b minus a by n. I was thinking b minus a by n, I write it down something else. Okay. So what we are doing whenever we want to find out left Riemann sum, right Riemann sum, or mid Riemann sum, first thing we need to do is divide the given interval into some regular parts. Okay. So here, if we have in general a closed interval a comma b, and if we want to divide it into n regular parts, the length of each subinterval will be b minus a by n. Okay. So for example, if you want to divide close interval 0 to 5 into 5 regular parts, then the length of each part will be 5 minus 0 by 5, which is nothing but 1. So that means we have interval 0 comma 1, then 1 comma 2, then 2 comma 3, then 3 comma 4, and then 4 comma 5. These will be the 5 regular parts of the closed interval 0 comma 5. Okay, so this is the first step we need to do whenever we need to find out left Riemann sum, right Riemann sum, or mid Riemann sum. First thing is divide our interval into n regular parts. And after that, what we will do, we will select the value of function according to the Riemann sum. So for example, if we have, close interval a comma b divided into n regular parts, with intervals like a comma x1, then x1 comma x2, up to and so on, xn minus 1 comma b. Okay, so then the left Riemann sum, the left Riemann sum is nothing but the value of function at the left endpoint of each subinterval, right? So here, what is the left endpoint? So this a is the left endpoint, x1 is the left endpoint, and xn minus 1 is the left endpoint. So we'll take the value of function at each left endpoint of each subinterval, and then the what you can say, the length of each subinterval, and then sum it. That will be your left Riemann sum. So here the left Riemann sum will be the value of function at left endpoint. So here left endpoint is a, right? So that is f of a, and then f of x1, and then f of xn, and into the distance of each subintervals. So this distance we simply write is at del, right? So here del is nothing but x1 minus a, which is same as b minus a by n. And why it's same? Because we are dividing interval into regular parts. That's why. So the left Riemann sum will be f of a plus del, plus again the left endpoint, that is f of x1 into del, plus f of x2 into del, plus and so on, plus f of xn minus 1 into del. Okay, so here since we are taking left Riemann sum means value of function should be left end point of each subinterval. Now what will be the right Riemann sum? The right Riemann sum will be right endpoint of each subinterval. That is f of x1 into del, and plus f of x2 into del, and plus and so on. At the end, we have f of b into del. And what will be the mid Riemann sum? Mid Riemann sum means midpoint of each subinterval. Okay, so midpoint, how can we find out the midpoint? Taking the average of each values, right? So that means the first will be f of a plus x1 by 2 of del, then the value of function at the midpoint means x2 plus x1 by 2, right? This is the midpoint of any any interval, right? If you want to find out midpoint, that means average of that two things, x1 plus x2 by 2, right? Plus and so on into del. At last we have f of b plus f of xn minus 1 by 2 f of that into del. So it means mid Riemann sum means we have to consider the midpoint of each subinterval and then find the value of function at that point. Okay, so these are the three Riemann sum: left Riemann sum, right Riemann sum, mid Riemann sum. First thing we need to do is divide our given closed interval into regular parts using the length, whatever length is asked to us. Finding the length is nothing but b minus a by n we have to consider. And then if you take the left endpoint of each subinterval, you will get the left Riemann sum. If you take the right endpoint of each subinterval, you will get the right Riemann sum. And if you take the middle point of each Riemann sum, you will get the mid Riemann sum. Okay, so now let's take one example here. So find the left, right, and mid Riemann sum of the function f of x is equals to, let's take very simple, suppose x plus 4. When, and the interval is when the closed interval 1 to 6 divided into 5 regular parts. Okay, so here what will be the left Riemann sum, what will be the right Riemann sum, and what will be the mid Riemann sum. Okay, so I'll give you guys 5 minutes to find out these three values: left, right, and mid. Once you find out the values, just answer me in the chat box. So it's 5:12. So let's take up to 5:17. Because after this, we just have definite integration, indefinite integration. That won't take much time. So just sit down and find out the values of left, right, and mid Riemann sum of the given function. F of x is equals to x plus 1. Okay, so let's see what will be the answer. So first thing is we need to divide the closed interval 1 comma 6 into 5 regular parts. Right? So what will be the length of each regular part? So length of each part will be b minus a by n. Right? So b minus a by n means 6 minus 1 by n. So the value of n is here 5. So it is nothing but 5 by 5. So we are getting 1. That means the length of each subinterval will become 1. So what will be those subintervals? 1 to 2, then 2 to 3, 3 to 4, 4 to 5, and 5 to 6. So now these are our subintervals. Now what will be the left Riemann sum? So left Riemann sum says take the left endpoint of each subinterval. So that means f of 1 into 1. So here the value of del will become 1. So whatever value here you will get, that is the value of del. Right? So whatever what will be the length of each subinterval, that is the value of del. So here the value of del is nothing but 1. So the left Riemann sum says the left endpoint of each subinterval into del plus and so on. Right? So here f of 1 into 1 plus f of 2 into 1 plus f of 3 into 1 plus f of 4 into 1 and plus f of 5 into 1. So what is f? So f is nothing but x plus 4. So f of 1 will be 1 plus 4 will be 5. 2 plus 4 will become 6, 3 plus 4, 7, 4 plus 4, 8 and 5 plus 4, 9. Okay. So the sum is nothing but 35. Right. No? So 20, 30, 35, I guess. So this will be our left Riemann sum. Now similarly, we can compute the right Riemann sum. So right Riemann sum says the right endpoint of each subinterval. So here the right endpoint is nothing but 2, 3, 4, 5 and 6. So that is f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6. Okay. So which is nothing but, did I miss? Yeah. So 2 plus 4 is nothing but 6. 3 plus 4 will become 7, 8, 9 and 10. So this will become 40, right? Because all these things are 30, 30 plus 40. So the right Riemann sum will become 40. Now what will be the mid Riemann sum? Mid Riemann sum says take the middle point of each subinterval. So now if we have the interval from 0 to 2, so the middle point of this interval will become 2 plus 1 by 2, which is nothing but 3 by 2, right? That is 1.5, right? So if you have 0 to, if you have 1 to 2, the midpoint will be 1.5. Right? Similarly, if we have 2 to 3, the midpoint will be 2.5. Okay. So you can compute this by 2 plus 1 by 2 also, which is 3 by 2. So the mid-Riemann sum says the value of function at midpoint of each subinterval. So that is f of 1.5 plus f of 2.5 plus f of 3.5 plus f of 4.5 plus f of 5.5. Right? Because the last interval is 5 comma 6. So the midpoint will be 5.5. So the value of function at these points is nothing but x plus 4. So 1.5 plus 4 will be 5.5, 6.5, 7.5, 8.5, 9.5. Okay, so we know that the sum 5, 6, 7, 8, 9 is nothing but 35. So this will be 35 plus 1 plus 2 plus 2.5, which is 37.5. Okay. So ultimately, the mid Riemann sum is nothing but 37.5. So you can compute left Riemann sum, right Riemann sum, mid Riemann sum of any function using the same strategy. First thing is divide your interval into given regular parts. Find the value of del from there. Okay, so here in this question we have del is equals to 1. But it is possible to get the value of del different. That is 2, 3. Depends on the question, right? So in place of 1 comma 6, if I given that, divide the interval 1 comma 6 into, or in place of that, if I given 1 comma 7 into 3 regular parts, then the value of del will become 2, right? So depend question to question whatever the value of del we have. And then you have to consider the value of function over the left, right and mid point of each subinterval and find the value of each Riemann sum. Okay. So now using the limit of Riemann sum, we define definite integration, right? So we know that the definite integration a to b f of x dx is nothing but limit n goes to infinity of Riemann sum of divided into n regular parts of a function with the with we what yeah of a function, or we can, as we write down in our lectures, that f comma a comma b are n. Okay, so this formula we know, and the limit also. Actually, it's kind of difficult to find the integral in the definite integration using Riemann sum. Okay, so what we will do, we will find left Riemann sum, right Riemann sum, and then we will apply limit n goes to infinity. And if that limit converges, we say that the integration a to b is nothing but the value of that limit. Okay, but it's a huge process, it's a very difficult or long process, so we won't go there. So stick to the basic computation, that is left Riemann sum, right Riemann sum, and mid Riemann sum. These things you should know how to compute these 3 points. Okay. So now let's go to the some uh, relation between definite integration, indefinite integration, and fundamental theorem of calculus, and then integration by parts and method of substitution. Okay. So first thing is fundamental theorem of calculus. So fundamental theorem of calculus relates indefinite integration and definite integration. So first of all, what is this antiderivative means? So antiderivative means a function whose derivative is the given f. So suppose that capital F dash is equal to small f, right? Then this capital F is known to be the antiderivative of small f function. For example, if you take small f as 3x square, then this capital F can be x cube plus 1, this capital F can be x cube plus 2, and so on, right? Because if you take f dash, you'll get 3x square. Here also if you take f dash, you'll get 3x square back, which is our small f, right? So here it's kind of obvious that antiderivative is not a unique thing. So, but whatever antiderivative we will get, that antiderivative is also known to be the indefinite integration. So that means the integration of f of x dx is this capital F of x function. So that means if you compute integration of 3x square dx, the answer will be x cube plus c. Now here the value of c is undetermined. So we can take any real number as a value of c, still it makes sense. Okay. So this is known to be indefinite integration. Now, fundamental theorem of calculus actually relate definite integration with indefinite integration. It says that if we have a function, the integration a to b f of x dx is nothing but capital F of b minus capital F of a. Right? And what is the f function? So here this f dash is nothing but small f. That means capital F is nothing but antiderivative of the small f function. Okay. So this is known to be the definite and indefinite integration. Now let's go to some methods about first thing is the method of substitution, and then we'll go to method of integration by parts. So both things we discussed already. So substitution method. So substitution means we are substituting a function. We try to simplify our given integration by some substitutions. For example, if you have an integration of the type that e to b f of g of x into g dash of x dx, right? So then here what you can do, you can take that t is nothing but g of x, and then dt is nothing but g dash of x into dx, and we can change this integration into some simpler one, where the limit will be from now g of a to g of b, because if x is equals to a, then by this thing we know that t is nothing but g of a, and if x is equals to b, then t is nothing but g of b. So the limit will change from g of a to g of b. Here we have f of t, because we replace g of x by t, and g dash of x dx with dt. Okay. So we can simplify the integration by using some substitution, and this method is known to be method of substitution. So here you have to judge which function you need to substitute to make it simpler. Okay. So we'll also take one example of this method of substitution too, but let's also discuss what is the integration by parts. Okay. So integration by parts means, as we know how to find out the derivative of product of two functions, but in place of derivative, if we have integration, how can we find out integration of product of two functions? So it depends on the functions too. So if we have some simple function, we can take that function and use integration by parts to solve it. For example, if we have to find out integration of some f of x into g of x dx, as integration is from a to b, then this is same as f of x integration of gx dx, and then we'll apply limit a to b, and then minus of integration of f dash of x integration g of x dx, and the whole thing over a to. Okay, so this is the formula we have learned in our high school high standards, but this thing also we can anticipate it as in terms of antiderivative. Okay, so what is that antiderivative formula for integration by parts? So let's see. So in terms of antiderivative. Okay, so it says that the antiderivative of this capital F of x is ux vx minus the antiderivative of u dash of v of x. Right? Here the small fx is nothing but ux into v dash of x. So here you kind of observe that this is the antiderivative of, or this whole thing. This whole thing is actually the antiderivative of f of x into g dash of x, right? And this whole thing is our ux into vx itself. So you can interpret integration by parts with antiderivative too, but whenever we want to solve the question, we can use our old integration by parts only. We don't have to go for antiderivative and all stuff. We can simply use our method, whatever we have learned so far, and then get the answer. But there are certain things which you want to consider. So the choices of u and v, u of x and v of x. Okay. So here, what are the function we need to choose in place of u and v? Okay. So here, in place of u of x, we'll choose those functions whose derivative is simpler. Right? For example, if I give you f of x is equals to some x cube into e to the power x, then the obvious choice for ux is x cube, right? Because the derivative of ux will become 3x square, right? And if you again derivated it, it will reduce in some manner. And if you take the integration of e to the power x, it will become simpler, right? Because e to the power x is its own derivative. So here, if you take v dash of x to be e to the power x, then your vx is nothing but e to the power x itself, right? So the choices of u and v depend on which function's derivative is much more simpler. Okay. So this is all about integration by parts. Is there any doubt in any of this method of substitution, integration by parts, or anything so far we have discussed? It's all clear? Okay, so let's solve one. Okay, one more thing I want to introduce is improper integrals. Okay, so suppose if we have an integration of this type, some integration from a to infinity, f of x dx. Okay, so if we have such type of integration, how we can tackle those integration? So what we will do, we will convert this integration into integration plus limit type of thing, right? So we can say that this integration is same as, the size same as limit from b going to infinity, integration a to b f of x dx. Okay, and then find the integration and apply the limit. Okay, so that's how you can solve the integration of the type integration a to infinity, or infinity or some a to minus infinity, and so on. Okay, so let's take one example. Is there any doubt in this thing? How can we change the integration with infinity into simpler one? Just take it to be b and then apply limit b tending to infinity over this particular integration. It will be same as integration e to infinity f of x dx. Okay, is that clear? This thing? They are known to be improper integrations. Okay, so for example, if I want to find out integration minus infinity to 1 e to the power x dx. Okay, then what will be this? So first I'll change this minus infinity thing into some finite quantity. So I'll take it simply that limit a going to minus infinity integration a to 1 e to the power x dx. Right, now I know how to find out integration e to 1 e to the power x dx. This is same as limit a going to minus infinity. The integration will be e to the power x, limits will be e to 1. And this is same as limit a going to minus infinity, and it will become e to the power 1 minus e to the power a. And now, over this quantity, we can apply our limit. So this is same as, if we apply limit over e, since it's a constant, it will stay as it is, limit won't affect it at all. So we will get e as it is, and then we will apply limit over here. So this is minus of limit a going to minus infinity of e to the power e. Right? So we know that, since we know by the graph of e to the power x function, this is the graph of e to the power x function. And we know that as x goes to minus infinity, e to the power x goes to 0. So that means this limit is nothing but 0. So the answer will be e. Okay. So we can handle those type of integration just by making it as a combination of limit and integral. Those type of integration are known to be improper integrals. And we will also study those integration in future too. Okay. So that's all from my side. I have, I think I have covered almost all the topics. So let's recall once what we have done so far. So we started with some basic definition of series. So what is a series? How to get a convergence and divergence of a series using 3 tests. We have comparison test, root test, ratio test. So we'll apply those tests in a series, in a particular order. So that means first we will see limit n goes to infinity, n is equals to 0 or not. Then go to comparison test, then go to ratio, then go to ratio test, root test, and then comparison test. After that, we have shown power series. So for computing the radius of convergence of a power series, we have the root test. After that, we have seen the Riemann sum and some properties of integration. Okay, so here is one question, you can solve it, but I think it's kind of easy one to solve this integration. Integration 0 to 1, x e to the power x square dx. Here you have to apply both things, the method of substitution. Now only one thing, you can apply a method of substitution and find the answer of this question, right? Just substitute x square to be equal to t. Then you will get 2x dx is nothing but dt. So x dx will convert into dt by 2. So now this integration will change into some simpler one, only in terms of e to the power x. So you can get your answer too. Okay. So yes, so that's all I have. I'll upload this and the previous PDF over the calendar today only. Then you guys can go there and download it. So if now we can talk about some of the doubts. So if you guys have any doubts, you can ask now. Yeah, tomorrow's session is for qualifier rerunner. So whoever is attempting to this reattempt qualifier, they can join tomorrow's session. We will discuss week 1 to 4. I think the announcement has sent to everyone. Maybe that's the...
Oh, ma'am, can solutions for week 8 graded and practice be also uploaded?
Yeah. So I'll upload by today.
Okay, ma'am. Ma'am, and one question in graded assignment 8, question number, the graph question, where we have a question about the negative area. Now,
Okay.
in one of those graphs, there is an area below the x-axis. Now, that is considered as a negative area, right? But
Yeah.
the answer is only two questions, only two options are selected as negative area.
Ma'am, actually, I also had that doubt, ma'am. It did not clearly mention that whether it is the total area negative or is that according to the English of the question, actually that option should also
Okay,
be
okay,
correct.
okay.
But then
Yeah.
but I did not select the third option, thinking that it would generally mean that the total area would be negative. So I did not select the third one.
Yeah, I think this is the question that we share my screen.
But I also had the difficulty, ma'am, because they did not mention the total area. They just mentioned like select
Negative
all
area.
the graphs with a
Yeah.
negative area, and that had a negative area. But they meant total area as negative.
Yeah, I think they meant total area is negative.
Yeah, ma'am. This question. So I had selected 2 and 4, but I had also selected one of the others. I think it was number, uh,
Hmm.
yeah, number 1 also. So now here it goes below the x-axis.
Okay.
So that's also considered a negative area, right? In figure 1, curve 1.
Yeah, so actually curve 1, the area of this portion will be much more larger than this area. So if you add it, this won't get you the negative area.
Yes, ma'am. But
Won't get
usually
you.
the question mentions it as like the total area, but here it just
Yeah.
tells that enclose a negative region, and then it
Mm-hmm.
actually encloses a negative region.
Right.
Yeah, this
But
enclosed
it is
word
just
should
a
not be.
English mistake. So,
Mm-hmm. Yeah, actually.
but I did not select the first option, thinking it will end up like this.
Yeah, I had selected
Mm-hmm.
it, so I got the entire thing wrong.
Wrong, right? I have entire thing wrong because
Yeah.
it's an MSQ question. So let me see. I'll try to give some partial markings too.
Okay, ma'am.
Let's see.
Okay.
But thank you for pointing it out.
Thank you, ma'am.
Also doing it. Okay. Anything else?
Ma'am, so if we receive such a similar thing in exam, we can be sure that it will always mean the total area, right?
Yeah, I always mean the total area.
Okay, ma'am.
They should have. So the difficulty of reattempt qualifier will be similar to as qualifier. We have attempted qualifier, whatever level that question paper was. A little bit some yeah. It kind of all similar to. Tomorrow's session is only for reattempt qualifier. So whoever haven't qualified yet, they can join the session because we will discuss from week 1 to 4. But since the quiz 2 is very near, I think you guys should focus on week 5 to 8 who have already qualified. Compared to qualifier, it will be a little easy, but kind of similar only. Okay, anything else?
Ma'am,
Yes.
yeah, for the quiz 2, what can I expect there? Not
So
exactly the
for
questions, but the